Pandas data frames provide several flexible means of indexing into subsets of our data. Let's start by importing Pandas. We then read in a small data frame of sales data. The simplest indexing style uses square brackets, just as we would use to index Python lists and NumPy arrays. For example, in the code shown here, we select with left bracket, column label, right bracket first, followed by left bracket, row label, right bracket. Thus, here we select salt, sold in January. Columns may also be referred to as attributes of the data frame if their labels are valid Python identifiers. Here, we select eggs sold in March with df.eggs, left bracket, March, right bracket. A more efficient and more programmatically reusable way of accessing data in a data frame is by using accessors. These include .loc and .iloc. The difference between the .loc and .iloc accessors is that the former accesses using labels and the latter using index positions. Both accessors use left bracket, row specifier, comma, column specifier, right bracket, and syntax. For instance, here we select spam sold in May using df.loc. On the other hand, here we select the same entry using .iloc 4,2. Remember, list and array type structures in Python use zero-based indexing. When using bracket indexing without the .loc or the .iloc accessors, the result returned can be an individual value, a Pandas series, or a Pandas data frame. To ensure the return value is a data frame, use a nested list within square brackets. As an example, this call uses a list of column labels, salt and eggs, to subselect a data frame with those two columns only. Notice we swapped the order of these two columns relative to the ordering in the original data frame in the selection. Use the exercises to get some practice now in basic indexing with .loc, .iloc, and with brackets. Let's look now at slicing data frames. Remember, we're still using our sales data frame. We assume that Pandas has already been imported as PD. The basic indexing here picks a column by default. The result returned is actually a Pandas series. A series is a one-dimensional array with a labeled index, like a hybrid between a NumPy array and a dictionary. Another way to think of a data frame is a labeled two-dimensional array with series for columns sharing common row labels. Slicing can be performed with or without accessors. Having worked with Python lists, we're familiar with the colon syntax for slicing. For instance, we remember positional slicing is half open, so slicing 1:4 extracts positions 1, 2, and 3 indexed from 0. Thus here, we extract the eggs column as a series and then select those 3 elements from the series. Pandas extends this colon syntax to allow labels in slices. Here, the first colon selects all rows. The slice eggs salt selects both columns eggs and salt. This is a potential gotcha with slicing with labels and the .loc accessor. It includes the right endpoint, unlike positional slicing seen so far. This example is similar in using the .loc accessor to slice all columns in some rows. The first slice, Jan:April, extracts all 4 rows corresponding to January, February, March, and April inclusive. The second bare colon is a universal slice selecting all columns. This example extracts a block with a proper subset of rows and columns, from March to May inclusive and from salt to spam inclusive. Using .iloc is very similar to using .loc, simply with positional integers specifying slices rather than labels. Here, we extract the same slice as before using .iloc. From row 2 up to but not including row 5, and from column 1 to the last column. Remember, Omitting the explicit start or end in a slice means we slice from the beginning or to the end, respectively. Both the .iloc and .loc accessors can use lists in place of slices. Here is an example of using .loc and a list of 2 columns. Here's another using .iloc and a list of 3 rows. Remember, with .iloc, the column slice 0:2 selects only 2 columns. Here's an important subtle distinction to understand. Selecting df, left bracket, eggs, right bracket, yields a series from the column labeled eggs. Selecting df, left bracket, eggs, right bracket, returns the data frame consisting of a single column, namely eggs. Many, but not all, operations are shared between data frames and series, and a series is always only one dimension of labeled data. Now that you've learned Panda's slicing idioms, here are some exercises for you to work on. We've previously seen how indexing and slicing works with Panda's data frames and series. Filtering is a more general tool for selecting part of the data, not based on labels or positions, but based on properties of interest of the data in itself. Data frames have several special methods for filtering. Underlying filtering is the idea of a Boolean series. Here, we ask where in the salt series is the number of sales recorded greater than 60. The series returned has true or false values according to whether the salt sold in that particular month was more than 60 units. In itself, a Boolean series isn't that useful, but when it is used to select from a series or data frame or array, it is very powerful. When used to make a selection, a Boolean series is called a filter. A filter may be used directly between brackets as a logical expression, or it may be assigned to another variable. In this case, the explainer variable enough salt sold. Filters can be combined using standard logical operators like AND, OR, and NOT. Here, we combine the filter salt bigger than or equal to 50 with the filter eggs strictly less than 200, first using AND, so both have to be true, second using OR, so either can be true. Notice the use of parentheses to enforce order of logical operations. Missing values are commonly encountered in data analysis. These missing values are sometimes represented by zeros, at other times by the special NaN, not a number value. Here, let's copy our data frame and add a column bacon with some 0 elements. We'll use this new data frame, df2, to explore Panda's methods for selecting or excluding data slices with zeros or nans. For instance, we might ask which columns have all non-zero values with the method all. This selection excludes the bacon column because it has 0 entries. We might also ask which columns have any non-zero entries. In this case, there are no columns of all zeros, so all of df2 is returned. A related question is which rows or columns contain NaN. We can ask that with isNull and notNull. Combining any and isNull returns any columns that have a NaN value. Conversely, we might want all columns where all data is present. That is, there are no NaN values. We can combine all and notNull to get this from the original data frame df. We can also remove rows with missing data using drop NA. Using how equals any, the row may is dropped from df because it does have a NaN entry. By contrast, how equals all would keep this row. Filtering can be powerful when used to assign values. We might select the egg sales for those months in which the salt sales are high. Explicitly, we extract the eggs column from df and filter the indices where the corresponding entry of the salt column is larger than 55. The result is a series subselected from the eggs column. This filtering allows us to calculate one column based on another, in whole or in part. Based on a filter on one column, we can modify the value in another column. For example, perhaps with every large salt sale, a few eggs are thrown in for free. It's your turn now to practice using filters with Pandas series and data frames in the exercises.